Hey, welcome back, Mr. Kolazar's class. Today we're going to be looking at the two ways that matter can change. So as we're working today, we're going to look at physical changes and we're going to look at chemical changes, the two ways that matter can change regularly. So our first one, physical change. We're going to look at material changing, which it alters a substance without changing its composition. So the substance still has the same chemical makeup beginning to end. Physical properties might change, but what we're looking at here is a substance is still the same material, it's still the same chemical makeup as it changes. A good definition for this, just to write at the bottom of the page or somewhere to include, is a change in size, shape, or state of matter, which means a phase change. So it still chemically is the same, but we might see it as a little bit different size or shape or state of matter. If we were to look at states of matter, the phase changes, transition from one state of matter to another, but the composition is still the same. Haven't changed the composition. So example would be like water's a good one. So if we melt water or freeze water, we'd go solid to liquid or liquid to gas. Now all of these are reversible. So we could go back and forth, melt or freeze, freeze or melt a substance. Vaporize or condensate. To vaporize would be go from a liquid to a gas, or condensate gas back to a liquid. Sublime and deposition. Sublimate would be to go from a solid to a gas. Deposit or deposition would be to go from a gas to a solid. A good example for this one is dry ice. The reason dry ice gets its name is frozen carbon dioxide goes right from a solid to a gas, so there's no water or liquid left over in between, so that's where it gets its name dry ice from. It's very cold, but there's no liquid mess as it goes from a solid to a gas. The other way we can change matter is to alter the actual composition. A change that alters a substance by changing its chemical composition. So we're actually making a brand new material afterwards. So you'll hear a lot of different terms throughout the year. A couple of them we'll talk about: to decompose, to rust, to explode, to oxidize, to tarnish, to ferment, to burn, to rot, to digest. Anytime we get a new composition, the material is brand new or different from before, is signs of a chemical change occurring. Some evidence of a chemical change. These are very important ones. If we change color or temperature, as we're getting the fall time, if the leaves change from green to, the yellows, the golds, the browns, the reds, chemical change occurring as we change in color. If we change temperature, so if the substance heats up when they're mixed together or cools down, change in temperature. If we produce light, good example would be glow sticks. Chemoluminescence is producing light by chemical reactions. If a new material is produced, that's probably the key one there, as we're going that new material produced, we talked about above, if it's different composition that we had before to afterwards. Formation of a gas. Hydrochloric acid and zinc bubbled to produce that gas. Baking soda and vinegar produce a gas, so produce a production of a gas. A new odor. Now the odor has to be new. If it smelled before and it still smells afterwards, that's not a sign of a chemical change. Now if we were to take and say when you bake a chocolate cake, towards the very end of the chocolate cake being made, you can smell that new chocolate cake production, and that shows a sign that there's a chemical change occurring from the beginning when the ingredients are mixed until the cake is produced afterwards when it's been cooked. So new odor. Fireworks is a good example here also. You can smell the burnt fireworks after they've been lit. Sulfur and the other compounds that are in there, they smell different afterwards than they did before. And then formation of a precipitate. Let's say you had two materials and you add two solutions, so they both start out as liquids, into our beaker. And as you add those two materials in, you get kind of a solid, chunky material at the bottom. That solid material is known as a precipitate. So formed in solution when they're made there, it's a brand new material being produced. So I'd like you to pause for a moment to work through these examples here, and then afterwards to unpause, and we'll go through to make sure that you're on the right track. All right, so after you went through these, first one, silver spoon tarnishes. As we're going a silver spoon tarnishing, we have a new material produced. The tarnish is basically when the silver reacts with the sulfur in the air to make a new material. So chemical change produced. So as you explain each one of these. Crushing an aluminum can. You still have aluminum, it just looks a little different size or shape-wise. So physical change, still have the same material before and afterwards. Freezing water. You start out with water, state change or phase change, physical change. You still have water afterwards beginning to end, so it still is H2O. One of the ones sometimes we get confused with is when we boil water and it goes from a liquid to a gas, it's still water. So if you boil water, it's still a physical change. Burning of wood. Afterwards, the wood is different than before. Light was produced, heat was produced, new material produced, all of those signs, chemical change. Copper turns to a greenish color. Copper reacts either with air or chlorides, many other things, and it'll change color from its kind of red-brown to kind of a greenish-blue color. Change in color, chemical change. And if we were to make your morning coffee and grind up those coffee beans, it's still the same chemical material. We've just changed the size and the shape of it. So physical change. So we'll be seeing many examples that you'll have to define as either chemical, physical changes. Now as we're going, chemical reactions is a big part of chemistry. So we'll begin to start looking at how they're set up and what they're trying to explain. So our first one here, just as a practice, iron reacts with oxygen in the air to produce rust. So one of the big combatants, we're always trying to stop things from rusting. So how can we stop oxygen from reacting with iron is going to be seen. To write this chemical equation out words-wise, iron plus oxygen is another way to show reacts with. To produce, our arrow symbol here is to produce rust. And we'll talk about rust later on is going to be the chemical iron 3 oxide. If we wanted to see what iron 3 oxide looks like, it's Fe2O3. Now that'll be something that we're going to be writing and working on throughout this year. The reactants to this problem. Reactants are what we start with. Our reactants in this case, iron and oxygen were a beginning part, and our products are what we end with. In this case, we ended with rust, which is known as iron oxide. So as we're going, that would be just a basic beginning chemical reaction. Now during chemical reactions, we have what's called the law of conservation of mass. It states that we're not going to create or destroy matter during a chemical reaction. What we call it is conserved. We don't gain and we don't lose matter. Now this is important because if every time we did a chemical reaction we gained a couple atoms, eventually the world would fill up and we just have too much material. Or if every time we lost a couple atoms during a chemical reaction, eventually the entire world and everything in the universe would eventually just disappear. So the mass of the reactants, what we start with, must equal the mass of the products afterwards. So if you start out with 16 grams of water as a liquid, 36 grams of water as a liquid, and we actually need, in order for this reaction to happen, some electricity. We'll see this example in class. And as electrical current is added through that, it will actually separate water into hydrogen gas and oxygen gas. Now the key part to this is if we started with 36 grams, we're going to end 4 plus 32 is 36 grams of total mass afterwards. We can't gain or lose mass. It only will simply move from one form to another. And our last problem, if we were to take 10 grams of mercury 2 oxide as heated, the mass decreases. Pure mercury remains in the container and it has a mass of 9.26 grams. The following word equation describes the reaction. Mercury 2 oxide produces mercury plus oxygen. Now the problem is We started with 10 grams, and we have now 9.26 grams of mercury afterwards. What we don't see is that we still have oxygen, which has escaped into the atmosphere. So what accounts for the loss of mass? That oxygen has went up into the air somewhere. So it's still mass, we just haven't collected it or contained it. So find out the mass of this material, how much oxygen we have left over. So if we were to take that 10.0 and minus that 9.26, how much material would we have left over is the question. And in this case, we have about 0.74 grams of O2 or oxygen produced. So law of conservation of mass is the idea that we can't gain or lose material from beginning to end of the reaction. We'll be doing many physical and chemical changes during class to continue looking at this.